Well, hello folks. This is Mr. York, your BC Calc teacher, and I'm excited to be able to give you the first video lesson. This is actually the first video lesson I've ever made, so hope this goes well. Hopefully at this point you've already looked through the review assignment and also the lesson on funky factoring, which is kind of a goofy name, but an important algebraic concept that we're going to use a number of times, and I really want you to be comfortable with. All right, so hopefully you're having a great summer, and this is easing you back into some of the math that you're going to be doing. We're going to be going at a pretty quick pace as we get into BC, but not a problem because you guys are the best and the brightest of our math students, and the pace should be just fine for you. However, if you find yourself stuck on anything that you run into in these summer lessons and assignments, feel free to email me. You can get a hold of me on the ed line, a_York at saratogaschools.org. I'll check my email periodically early in the summer, and then as we get towards the end of the summer, I'll check it pretty much every day. All right, so I'll be glad to respond to you, give you whatever tip you needed to be able to get through the issue that you're having. Okay? All right, so that you know, our textbook actually has a preliminary chapter and a chapter 1 that we're not going to do in class. Between the work you've done with the honors pre-calc and your summer work that you're doing right now, we're going to get through, we'll already be through that preliminary chapter in chapter 1, and we're going to open up day 1 with chapter 2. All right, so hopefully, if there's anything that you're uncomfortable with in terms of all this limit review that we're doing right now, you get in quickly that first week, because I'm going to give you a test on the material in chapter 1 in that review assignment, the start of the second week, the first full week of school, that is. All right, what we're going to start with in this lesson is a series of methods that we can use to find the limit of a function as x approaches a particular value, what we might call a constant. Now, as we go through this, these are what we call analytical approaches, which are very important to us. We can find, or at least get a real good idea of what limits of functions might be by looking at their graphs or looking at a table of values. And let me get this out of the way here. But those graphs and tables of values that we might be looking at to try to determine a limit of a function as x approaches a particular value are only ways of suspecting what we might get for a limit. And if we can use the analogy of the courtroom, it's one thing to suspect, but it's another thing to convict. Right? So we might arrest somebody who's a suspect, but we won't convict somebody unless we're able to prove beyond doubt that they have actually committed the crime. So in limits, I'll use that same analogy. We can suspect a limit, but until we do the work analytically, we can't really convict or prove beyond a doubt the value of that limit. All right, and so hopefully we're comfortable with the idea that when I'm talking about these limits, and I'll just give you a little quick sketch here. Say I'm letting my x value approach some number c, and I'll come from the left here. What I'm hoping from my function, if I'm looking for a limit as x approaches c, is that the function values approach a certain y value, a certain output, which I might call L. And if I approach from the right, get x is closer and closer to c from the other direction, that I also approach that value, that function value L. Okay, and if those left and right hand functions agree, then we say we have ourselves a limit as x approaches c. And notice whether I have an actual function value at c is not important. So we could have like a hole right here at c. It's not quite lined up, but hopefully I'm getting my point across, so to speak. Now, the best method, if we can use it, for finding the limit of function is what we call direct substitution. Now, direct substitution really would be the case where we don't have any sort of discontinuity. And we'll review discontinuities more in the next lesson. Right? But this would be a case where the function is defined at x equals 0. And if you approach 0 from the left and from the right, you're approaching the same y value. Right? And when we have that situation, plugging 0 into the function rule, as I've done here, allows us to figure out what the y value would be as we approach that x value. All right, so definitely the simplest way to go, but usually not a method that's going to work for us. We usually have to figure out another way to get things done. So another technique that we'll have to be comfortable with is called factoring. This is where you have a function rule where direct substitution would give you 0 over 0. Now, 0 over 0 is actually a fairly interesting situation to run into in the limit world, because that means really the limit could be anything. It could be infinity, it could be any constant number. So we're going to have to think of another way to do the work so we can find out what we're dealing with here for this limit. So I recognize here that we have the difference of two cubes. Now, we need to remember the factorization forms for the difference of two cubes as well as the sum of two cubes. The difference of two cubes factorization form, which would be the a minus b times a squared plus ab plus b squared, is used to come up with the factorization that I show you right here. All right? Now, by the way, the sum of two cubes would have this factorization form. Okay, so that would be the case where I'm trying to break down a to the third plus b to the third. Whereas in the case that we're dealing with in this problem, we're working on something of the form a to the third minus b to the third. So the factorization form is worked through, and now I have a common factor in both the numerator and the denominator. So I'll be able to reduce the fraction rule, or excuse me, the function rule, and I get a new function rule which is equivalent to the original function rule in every way except for we've actually gained an element in our domain. 3 was not a domain element in the original function, but now it is in our simplified function. What we really did is we plugged the hole that's in the graph of the original function. And now with this nice new simplified function rule, we can do direct substitution with the 3. And we're able to find that 27 is the function value we approach as x approaches 3. All right, so let's move on to a third method, rationalizing the numerator. And again, we're dealing with a situation where direct substitution would give us that 0 over 0 situation, what we call an indeterminate form. And we'll talk more about that later in the course. Now, this situation comes up sometimes when you're trying to do the limit definition approach to finding the derivative of a function at a particular value. And you may have already run into this form last year. But the technique that we use to get out of this 0 over 0 situation is to multiply the numerator and denominator by what we might call the conjugate of the numerator. Okay, so the conjugate form by just changing the sign of the second term in the binomial. And we're using that conjugate so that the product in the numerator actually turns out to be a nice expression, no square roots, um, that actually will end up being a factor that will cancel with a factor down in the denominator, right? So we're multiplying numerator and denominator by the conjugate to come up with an equivalent form of the original function so that we can cancel factors, similar to what we were trying to do last time in canceling factors, to get a simplified function rule where direct substitution will do the trick. Okay? Let's see, what do we have for the fourth method? Simplification. So now we have a function rule that is itself a complex fraction. And the complex fraction would give us 0 over 0 in this case if we let x equal 0. So direct substitution is not going to work for this limit. So what we do, the easiest way to handle complex fractions is to multiply the numerator and denominator by what we might call the least common mini denominator. All right, in other words, take each factor in a denominator of one of the fractions within the complex fraction and find the least common multiple. That's where the 4 times x plus 4 comes from. So I'm going to multiply both numerator and denominator by that expression. And I do need to be careful here. I have to distribute across that difference with the entire expression 4 times x plus 4. And so I get the product of 1 over x plus 4 times my new expression. And I get the product of 1/4 times my new expression. And then the difference is still there. Okay? And this allows me, I anticipated, this allows me to get a numerator now that has a common factor with one of the factors in the denominator. In this case, I get a -1-to-1 ratio. And now my simplified function rule allows me to do direct substitution again. And I'm able to get the limit as x approaches 0. All right, fifth method, expansion. And you're starting to see a theme here, hopefully, that other than direct substitution itself, we have a number of methods to handle the situation where direct substitution gets us into the 0 over 0 limit problem. And so with expansion, we're dealing with a function rule that has, well, in this case, a binomial raised to some power. And I picked this example because it's pretty common that we're going to have to expand a binomial to the third power. So for those of you who have forgotten, we had a quick way to do this. You would take the first term and raise it to the third power. Then add to that 3 times the first term raised to the second, and the second term raised to the first. Then you take 3 times the first term raised to the first power and the second term raised to the second. And then finally, you would just take the last term and raise it to the third power. Now, where did this come from? You might remember Pascal's triangle, and there's a 1, 3, 3, 1 level in that Pascal's triangle, and that's where my 3's came from. And then you should be able to see the patterns for the exponents that I've used in this expansion. So that's a binomial expansion, third power expansion, that you want to be able to do quickly. And that's where I got that numerator from. Okay, this is the expansion right here. So anyway, I do that and I simplify by recognizing the 8 and the -8 goes to 0. I factored out an x. And once again, I'm able to get factors to cancel that now allow me to do the direct substitution and define the limit value. Okay. right? And then the next one, the last of the ones that are really somewhat review for you, hopefully, is trig substitution. And like the last methods that we've been covering, direct substitution is going to get us into a problem. If I substitute pi over 2 in for theta, right here, I'm finding in the numerator that I'm going to be evaluating the sine of pi. Now, of course, the sine of pi is 0. And if I look at the denominator, the cosine of pi over 2, here's our cosine curve, pi over 2 is also 0. All right, we're going to do an awful lot of work with these trig functions, so you need to be adept at coming up with trig values at quadrantal angles, and as well as with angles whose reference angles are pi over 6, pi over 4, and pi over 3. So just be on your toes in that respect. So what I can do here is try to use a trig identity that allows me to make a substitution so that I once again can do some cancellation, get an equivalent function rule, simplified version, where direct substitution would work. This came from the double angle formulas that you'll need to have memorized. Then the cosine theta cancels in the numerator and the denominator, and now direct substitution allows me to get 2 for an answer. All right. So these are the methods that you need to be able to handle with ease in finding limits of function as x approach a constant. Now there is a 7th one, and that's using something called the squeeze theorem. And this is new for you. So what I'm going to do is go through the proof of a limit of a function using a squeeze theorem, but we have to talk about what that squeeze theorem is really all about. So let's do that first. All right, you'll notice I paused right there. It turns out that I didn't realize I'd claimed we were going to prove the squeeze theorem. I'm going to explain the squeeze theorem, and then we'll use it to prove a basic limit of that we're going to use a number of times. So let's get to what's the squeeze theorem, or what's also known as the sandwich theorem. All right, I've always learned it as the squeeze theorem, but there are a number of folks that refer to this as the sandwich theorem. And what this is all about is getting a function trapped between two other functions, both of which are heading to the same function value as x approaches c. So an example might be, let me give you some colors here. Let's say we have a function h that is always less than or equal to a function f. And let's see, I do something like that. So we're going to have h be the green and f be the black function. And my red function will be function g, which is always going to be function values greater than or equal to, and I'm drawing it just so that I can show that as the x values approach c, the y values for each of these functions would be approaching the same thing. So if we can argue that function g's limit as x approaches c is L, some value, and function h approaches that same function value as x approaches c from either the left or the right, together with the fact that function f's function values are always stuck between, if you will, the function values for h and g, then we can argue that the limit of function f must also be L. And intuitively, this is pretty straightforward. Now, when you read this, there is a phrase here that seems a little bit goofy. By the way, that symbol is the symbol for all, or a characteristic that's true for everybody. All right, so we can read this theorem as if h of x is less than or equal to f of x, which is less than or equal to g of x. In other words, f of x is a function value that's always between the function values of these other two functions for all x's in an open interval that contains our c. Right? So this doesn't have to be true for all values of x between negative infinity to infinity, but if you will, there's some sort of neighborhood of values of x around c where this inequality holds, with the possible exception of right at c itself. And you wonder, why do we have that qualification? Well, it turns out that even if there's a hole in any or all of these functions right at c, that hole will not disturb the left and right hand limits that are involved in our problem. And so the sandwiching or the squeezing with these limits still holds. Okay, so it's a pretty easy concept to pick up intuitively from just looking at a diagram, hopefully like the one I've drawn here. But let's try to use that concept to actually prove that we can come up with a limit as x approaches 0 of the sine x over x. Now, I'm not going to give away what it actually is, but we're going to be proving that this equals a particular number. Right? And it's going to take a little bit of trig and geometry to get us set up here. So let me introduce you to a unit circle, and the unit circle has an angle theta drawn in standard position, good old-fashioned trig, and I'm going to be referring to three different geometric areas here. One area is the area triangle AOB. Okay? Then I'm going to talk about the area of a wedge. Now, the wedge would be what we might call sector AOB. So instead of having a segment bordering this part of the area, it's going to be the arc or section of the circle. And then the third area that I'm going to be looking at is triangle AOC, this right triangle right here. Okay? I'm going to use these areas to work my way towards being able to prove the limit as x approaches 0 of sine x over x is equal to a particular value. So let's look at how we're going to come up with expressions for each of these areas. So first, triangle AOB, which was the blue one that I tried to graph in there. Now, a formula from Algebra 2 trig for finding the area of an oblique triangle, a non-right triangle, is 1/2 the product of two sides times the sine of the included angle. Okay, that was that K equals 1/2 AB sine C formula on your formula sheet. And so the two sides that I'm going to focus on are little a, that's the side opposite angle A, and little b, that's the side opposite angle B in this blue triangle here. And then the included angle would be theta. Now, because I'm working in a unit circle, it allows me to do a lot of things real quickly and easily. And one is to be able to recognize the radii of the circle are going to be 1. That's what it means to be a unit circle. So, an expression that I can come up with for the area of the blue triangle is 1/2 1 times 1 times the sine of theta. Okay, or just sine theta over 2. All right, so we'll hold on to that expression. Come back to it. Next, I want to look at the area of the sector. Now, I got a crazy looking expression here, but really what this is a fraction of the area of the whole circle. The area of the whole circle would be pi r squared. But I don't want the whole circle. I only want a portion of the whole circle formed by rotating the initial or the positive x-axis to its terminal position, ray OB, if you will. Okay, so theta can be thought of as the fraction of the full 2 pi rotation that I want to use to build this sector. So that is really the fraction of the full rotation and also the fraction of the full area. All right, so if you take that fraction of the whole area and reduce this, you'll get what might be the familiar 1/2 theta r squared formula that you may have seen before for the area of a sector when we're talking radians. All right, we'll use that formula again later in the course for a number of things. All right, so if that's going to be the area of our sector, and the r, the radius of the circle, is 1, really this simplifies down to 1/2 theta. All right, so we'll use that again in a second. And now finally, the third area, oops, I've lost my diagram here. The third area that I want to look at is right triangle AOC. And that's the easiest triangle of all to come up with a formula for. That's just 1/2 the base, which I happen to have a B there already, and then the height, which is the AC here. And the base part's pretty easy. That's radius 1 again. But the height, we'll have to do a little bit of thinking here real fast. Let's see, how am I going to get an expression that has h in it? Well, I'm going to think in the right triangle, this red right triangle, that the tangent of theta is the opposite to hypotenuse. In other words, the h is equivalent to the tangent of that theta. So this is 1/2 times 1 times tan theta. Okay? Now, clearly, from our diagram, we can tell the order of the magnitudes of these areas, right? In fact, the list of areas that I've worked on here go from least to greatest. Right? That's clear from our diagram. So let me flip to another page here. It's the same diagram, and I've just recognized which areas, or how the areas are related in terms of their magnitude. And I've put down the area expressions that we came up with using an extended inequality. And I say, why are there equals there? Well, if you had theta as 0 degrees, in other words, you didn't move the initial ray OA anywhere, then these would actually be equal to each other. Now also, if you went 180 degrees or pi radians, you'd have the same situation. So you could have equals, but kind of a silly case, I guess. So what I'm going to do is I'm going to take this inequality and I'm going to multiply through by 2. Right? So that's all I've done. And then I'm going to change tangent. Well, I guess I should help you out here. The tangent I'm thinking of is sine theta over cosine theta. When I see tangent, I see a fraction or a ratio. And I also understand that with inequalities, if you have fractions and you form their reciprocals, you will flip the inequality. Real quickly, if you have 5 is greater than 4, then 1/5 has to be less than 1/4. The greater magnitude, if placed in the denominator, will form a lesser fraction, in other words. So I'm going to take that tangent ratio and flip it. I'm going to take the reciprocal of theta, and I'm going to take the reciprocal of sine, and then the inequalities will flip. Now, I know where I'm going with this, You just need to make sure you understand why I can do each of these steps. Now, I'm going to multiply all three of these expressions by sine theta. Now, here's the problem. Depending on the size of theta, the sine of theta could be positive or it could be negative. Now, with inequalities, this presents an issue. When you multiply both sides of an inequality with a positive number, you would keep the symbol in the direction that you have it. But if you multiply both sides by a negative value, you're going to have to flip the symbol, we used to say. So we're going to have to break this down into cases. Okay, so we're going to look at what happens if sine theta is positive, that's greater than 0, or if sine theta is less than 0. All right. Now, I'll focus my attention on what's going on if sine theta is greater than 0 first, and then we'll look at what to do about what happens when sine theta is less than 0. All right. Now, when sine theta is greater than 0, we can multiply through, and the symbols will remain the same, and this turns out to be the extended inequality. Now, one thing I want to make sure you see a connection on is the sine function looks something like this, from negative pi over 2 to pi over 2, but the key idea is that the sine of theta is positive as x approaches 0 from the right, as long as we're in a fairly close neighborhood, fairly close to x equals 0. As we approach 0 from the right, the sine theta is positive. So for my work here, I'm thinking that the sine of theta is greater than 0 as theta approaches 0 from the right. Right? And that's the notation we used to say is we're approaching something from the right. So as I come down here, if I want to take a limit as x approaches 0 from the right of each of these expressions, my hope is that I can prove that the limits of the outside functions, the one on the left and one on the right, approach the same value or have the same value, thus forcing the middle function to approach the same thing as well by this squeeze theorem. And clearly, if you look at the cosine function, all right, something like this, as we approach 0 from the right with our angle theta, the cosine value is approaching 1. Direct substitution will give us that. Also, on the right, whenever you take the limit of a constant, you get the constant. It doesn't really matter what theta approaches. And so we've been able to show that the limit as theta approaches 0 from the right of sine theta over theta has to be 1 by this squeeze theorem. Okay? Now, the other case runs very similar to this. If the sine of theta is less than 0, if we look back at the sine curve over here, as we approach 0 from the left with our theta values, that's where the sine of theta is less than 0 or negative. And so when we multiply through with a negative expression, we'll flip the symbols here. But again, we've been able to get that sine theta over theta sandwiched between two functions whose limits are going to be equal, right? So again, on that cosine curve, as theta approaches 0 from the left, because that's where the sine of theta is negative, the cosine is approaching 1, right? And of course, The limit of the constant 1 is 1. And so we've been able to sandwich the left-hand limit between the same two values of 1. And because of the inequalities involved, we had to be careful and look at two different cases. But whether we're dealing with the left-hand limit or the right-hand limit, we were able to get the sine theta over theta sandwiched between two functions that have the same limit. So we've been able to prove that the sine of theta over theta has a limit of 1 as theta goes to 0. And the variable theta is not important. You could have the limit as x approaches 0 of sine x over x, and that'll equal 1. Okay. Now, based on that proof, we're going to be able to show that the limit of 1 minus cosine theta over theta is equal to 0 as theta goes to 0. Okay? And the trick to this proof is to multiply numerator and denominator of the original function by, well, it's kind of like a conjugate, really. 1 minus cosine theta, and what's really called a surd, 1 plus cosine theta. If you use that to multiply the numerator and denominator, you'll get a new expression where the numerator can be replaced right here. This 1 minus cosine squared theta can be replaced with sine squared theta. Another one of those trig identities. And the reason that's helpful is now you can break up the factors that make up this function whose limit we seek into pieces. Now, this might be worth talking about real carefully here. If you take the limit of a function that can be thought of as a product right, and that's what I'm trying to write here. Now you can't see it, but my head's making a big shadow that keeps getting in my way. But the limit of a product is the product of the limits. Usually. Now I say usually, there is one big caveat here. If the individual limits cannot be arrived at, in other words, you can't come up with values for them, then we can't say that the limit of the product is the product of the limits. The limit of the product is the product of limits that can be evaluated, that can give us constant values. Okay? So the breakup of this particular function as the product of sine theta over theta times this other factor allows us to use the limit that we just proved, right? The limit of sine theta over theta as theta goes to 0 is 1. And then we can use direct substitution here to find the limit of the other factor. And that'll give us 0. And since we're able to figure out the limit of each individual factor, the product would be the limit of the original product, which therefore gives us the limit of the original function itself. Okay, so you want to make sure you commit to memory. The limit, I'll use x this time, as x goes to 0 of sine x over x is 1, and the limit as x approaches 0 of 1 minus cosine x over x is 0. Now, you hear some people call those basic limit definitions. Now, I don't like calling them definitions because we just proved them. So I might refer to them as basic limit theorems. Right? Now, notice that based on that first limit, I'm getting a little messy here, but that first limit, if I have x over sine x, since that ratio approaches 1, it won't matter whether I have x above sine x or vice versa. It's still going to be 1. Right? Well, based on that, and we're almost done here, guys. I know this is a long lesson for summer. But let's just do a couple of things here to wrap this up and we'll be all done. All right. I ought to take a peek at how long this has been. Oh, 40 minutes. Oh my goodness. Well, hopefully you paused it a couple of times and took a break. But we'll get this done in 10 minutes here. All right, the limit of sine 2 theta over theta is one that we can figure out based on that first limit theorem that we've proven by sandwich theorem. But the key is we have to have the angle that we're taking the sine of, the angle that we have in the divisor, and the angle that is involved in approaching 0 agree. And they don't seem to agree here. We've got 2 theta as the angle we're taking the sine of, and the other ones are theta. Right? Now, this is not a big issue. If theta approaches 0, then clearly 2 theta approaches 0. All right? So sometimes I'll write under the limit other things that approach values based on the given condition. All right? So the only problem we really have is the fact that we don't have 2 theta down below. So that's a quick fix. What I'm going to say is that I can multiply top and bottom, numerator and denominator, by 2. And we were just talking about the limit of a product. I'm going to think of that as the product I'm taking the limit of, and the limit of the first factor is 2, regardless of what theta approaches. And then the limit of the second factor, because remember, if theta goes to 0, 2 theta goes to 0, that second limit will give us 1. We've proven it. And so the limit here for this problem is 2. Now what happens here is we think that we have the same situation as last time, but remember what we need to get to agree are the angle inside the sine, the angle in the denominator, and the angle that's going to 0. Well, here we already have that. We don't have to really do anything. We might want to rewrite as a product, oops, it's supposed to be a 0 here, sine theta over theta, and a 1/4 here, right? Because that's really what we're dealing with. And the limit of the constant is the constant, and the limit of sine theta over theta, as theta goes to 0, is 1, and so we get 1/4. Okay? Now let's see. What's going to happen with this next one? Well, again, this is an example where I'm going to be using the idea that x over sine x is going to be similar to sine x over x as x goes to 0. But I'm going to have to multiply the numerator and the denominator by 4 so that I can get these angles to agree. And again, if x goes to 0, 4x is also going to 0. So I can use our theorem once again. Let's see, I'm going to have a 4x. I'm going to have a sine x, a sine 4x, and I'm going to have this extra factor of 4 down here. So again, this goes to 1, and that's what we tend to do, so we don't have to keep writing these limit expressions out over and over. Is say, hey, this factor goes to 1, and this factor right here, yeah, it's constant, so it doesn't go anywhere. It just stays at 1/4. All right. So now we have something that doesn't seem to have, it's not as straightforward as the last ones anyway. And notice that I have a plus up here, so there's a right-hand limit. Right? So I don't know if that really made a difference or not. We'll have to see. But let me do a little substitution here, because I know something about the sine and maybe a cosine piece, but tangent not so much. So I'm going to change tangent to sine over cosine. And instead of multiplying by x, dividing by x, I will multiply by 1 over x. Oh, I see it now. Rearranging the factors will allow me to see one factor is sine x over x, And another factor is 1 over cosine x, right? Organize that a little bit more carefully for some of you. Maybe you don't see it immediately. Right here. All right. So we know this goes to 1, but we're not out of the woods yet. The other factor we have to be able to find a limit for. It's got to equal a constant, or this factorization or break up into factors isn't helpful. But it turns out that the cosine of 0 is 1. And so this goes to 1 as well, and we get 1. Okay. Well, it starts to get a little redundant here. Hopefully you recognize the situation here, that in order for me to get that angle down below, I'm going to have to multiply top and bottom by 3x. But in order to get the 4x above in the numerator, I'm going to have to multiply top and bottom by 4x. Well, it's a little redundant here. I didn't have to really do that much. I've got an extra factor of x numerator and denominator than I really need. But, oh, and also 3x goes to 0, and so does 4x go to 0. So this ratio right here goes to 1. This ratio, right? How's that for crazy circling? That goes to 1. And I'm left with the limit as x approaches 0 of 3x over 4x, or 3/4. Okay? So I bet you can look at that example, if you can sift through all my crazy circles, and come up with a plan for how to handle a situation like that. Right? The 3 and the 4, we can predict from the original form. And so we can build a quick rule should this come up again, and it's not really worth memorizing because it won't come up all that much. But the limit as x goes to 0 of sine bx over sine ax will just end up being b over a. Right? All right. And last thing, quite a lesson here. The last thing, take a look at the limit as x approaches 0 of x sine 1 over x. All right. First thing I want to do is help you recognize that we can't really use the tricks that we've been using on the previous problems to make use of the theorem that we've proven using the squeeze theorem. In order to do that, we would have to get this angle in the denominator. Well, we can do that. That's not a problem. Instead of multiplying by x, that's equivalent to dividing by 1 over x. So there they are. The angle inside the sine and the angle down in the denominator agree. Well, there's a third piece. We have to have 1 over x approaching 0. And hopefully it's clear to you that as x goes to 0, 1 over x doesn't head towards 0. In fact, it's going to go to infinity. And so we don't have the proper setup to be able to use that first limit theorem that we proved. So what are we going to do? Well, let's go back and see if we can do the sandwich theorem on this. And I won't go through a whole proof, but let's look on the calculator at the function y equals x times 1 over x. That's what I punched in there, and then I did zoom trig, right? Just to come up with a decent starting graph for my function. And I'm interested in what's happening to the graph as x approaches 0. Well, it's wiggling around kind of as we get close to the origin, so let's zoom in. And, you know, if you didn't have your calculator out, you might want to pause it right now and get your calculator out and catch up to us. This is kind of cool, I guess. I think it's cool. I think a lot of things are cool. So anyway, we zoomed in and there seems to be a decent amount of wiggling. It looks like it might be 0 maybe. I don't know. Let's zoom in again. I'm just going to keep hitting enter a few times. And what's interesting about this function is the more you zoom in, the more wiggles, if you will, the more up and down oscillation you're going to see. And after a couple of tries with the zoom, we start to realize that there's an infinite number of these oscillations between wherever we position ourselves on the x-axis and the origin. And no matter how tightly we go, it's still going to be an infinite number of these oscillations. This kind of stretches our understanding of what a limit's really all about. A limit situation is not declaring that the function is always closing in on a particular value, but that it is always being contained in an ever tighter neighborhood. What does that mean? Well, as my function approaches x, the function values themselves don't have to always be approaching the same value, which would be 0 in this case. They just have to get caught into a tighter and tighter neighborhood. Right? The width or the span of the neighborhood that contains the function as we approach 0 just needs to be tightening infinitely, if you will. That neighborhood has a span that approaches 0. All right, so that's a little bit beyond what you probably thought of in terms of a limit process. And what I'm going to do with the calculator here is give you a couple of functions that will define that ever shrinking neighborhood. Let's go back to y equals 0. There's the function that we punched in. And let's put in absolute value of x. Right, so we're going to go to math over the number. And the first option is absolute value. And if yours says ABS, that means you have the old operating system. By the way, if you have the old operating system, talk to me. We'll get you the new operating system. You'll be glad you had it. Right, so I'm going to put the absolute value of x as one function. And by the way, let's graph that right now. Don't worry about the fact that we zoomed over and over. Notice that the absolute value function is acting as a function that's greater than our original function for all x's, greater than or equal to. And the reason is the sign ratio can never get higher than 1. It'll be less than 1 quite often, but it has a maximum value of 1. Right? So the absolute value function will always have, well, you're wondering why I'm mentioning the sign ratio is always 1. Whatever that is right there, it could never have a sign ratio greater than the value itself. Okay, so that allows us to bound that function. Now, let me rephrase that. Okay, I'm almost done here, and I've almost screwed it up. That right there is what we can take the absolute value of to bound that function. All right, I have apologized there. I got myself turned around. I had to pause it and think about what I was trying to tell you. So let's try again. Right here, this is the piece of the function that gives us our upper limit. Because the sign value, regardless of this expression in here, has to be magnitude of 1 or less. So the product will be equal to x or less than x in magnitude. And that's what allows us to have the absolute value function bound it from above. And similarly, we can bound our original function from below with negative absolute value of x. Okay, so let me get that in there and do the graph again. And so we can run through a squeeze theorem proof to show that our function is always between the negative absolute value of x and the absolute value of x. Right? And it wouldn't be terribly difficult to make that argument. And therefore, the limits of these functions can be compared as x goes to 0 in the hopes that the sandwich or the squeeze theorem will apply. And we can clearly see that the absolute value of x will approach 0 as x approaches 0. And so we will be able to squeeze that limit between 0. Okay, so what we saw or suspected from our graph, which is an ever-tightening neighborhood that's going to force our function to have a limit of 0, is actually provable using the squeeze theorem. Okay, and actually when we use the squeeze theorem on the AP at the end of the year, if that comes up, all we need to do is argue what two functions we know bound our function, and the limits of those functions will be clear, and we'll be able to make an argument very quickly that we found the limit by the squeeze theorem. All right, so that does it for the lesson. I applaud you in being able to make it through nearly an hour lesson. That was, in past years, my opening lesson. But I felt like quite a bit of this was already review, and I wanted to do something a little bit more when we get together. You know, a little bit. I want to get into the new material a little bit faster. So we'll have one more lesson, one more video lesson on sections 1.4 and 1.5 in your textbook. And what I want you to realize is that the practice problems from this video and for the next video, whoops, I already did that, can be found online. All right, our textbook, we can't get the whole textbook online, but we can get to the problem sets. And in fact, the odd problems have the solutions worked out as well if you click on the S next to the problem number. So you can either click here, where it says here, or go to the web page, and I'll have another place where you can click here for your textbook. So you click here, and hopefully you'll get to your internet web. Let's see if I'm going to get to it. Hopefully you're faster than I am on this, or at least your computer. All right, it's trying. There it is. All right, and once you get this to come up, let me move this out of the way. All you have to do is change the section to the section you want to do your work. I don't know why I've lost this, where it went. But you'll see a place where you can pick what chapter and section you want to do, and then you'll be able to do your homework. All right, so we'll see you on the next video. Good luck with these problems.